Welcome to this next video in the playlist on vector spaces. In this video what we're going to do is introduce the concept of a dual vector space. Now the first thing that I should do is give a warning, and the warning is this: if you've just arrived on this video and haven't followed the previous videos in this playlist on vector spaces, then you will be able to understand this providing that you have seen abstract linear algebra before, okay? And I mean, you need to know the abstract definition of a vector space. You need to know the mathematician's definition of a vector space. If your concept of a vector is still just something with a direction and a magnitude, okay, a little arrow pointing in a certain direction with a certain magnitude, then you're not going to be able to understand this video. You must understand the abstract mathematical algebraic definition of a vector space as just a set of symbols with two composition laws defined on it. Okay, so that's the first warning, that this is going to be abstract and that you must know the abstract definition of a vector space before you can understand what a dual vector space is. Even if you do know what the abstract definition of a vector space is, the definition of a dual vector space is still very, very abstract and takes a lot of getting used to. Okay, so enough waffle. Let's actually begin with the concept of what a dual vector space is. Okay, so what we're going to start off with then is some vector space, capital V, and this will be over some abstract field, capital F. So we start off as usual with a vector space, capital V, over some field, capital F. What we are now going to construct is the dual vector space, which is also going to be a vector space over the field, capital F. Okay, so we're going to construct something called V star, which will be called the dual vector space, or just the dual space of the vector space capital V, or if you're really getting fancy, the algebraic dual space of capital V. Okay, but most people just call it the dual space. Okay, and this is going to be another vector space over the field capital F. Okay, so from one vector space over a field F, you can construct another vector space over the field F, and this other vector space is going to be called the dual vector space of this one here, and it's notated V star, like so. Okay, so that's lovely, but how do we actually do this? What is this thing that's underlined in turquoise here? Okay, well, the elements are going to be very, very abstract things. Okay, they're actually going to be linear maps of this vector space. Okay, and remember, we are thinking very, very abstractly. All this needs to be is a set of symbols with an addition law and a scalar multiplication defined on it. Okay, those symbols in that set can be whatever you like. Okay, so in particular, they can be representing linear maps of this vector space onto something else. Okay, and that's indeed what we're going to see they will be. So don't be alarmed when I first show you what the elements of this dual vector space are actually going to be. Okay, so a way that people often write this then is that V star is equal to the set. Okay, so we're firstly going to try and understand what this is as a set, then the rest of the video will be devoted to trying to understand how we're going to define an addition and a scalar multiplication over the field capital F on it. But firstly, the first challenge, the first hurdle, is just to understand this as a set. Okay, so as a set, it's the set of all algebraic homomorphisms, which in the concept of linear algebra, in the concept of vector spaces, just means linear transformations or linear maps. And because we're working over the field F, I will subscript F here, from the vector space capital V to the field capital F. Okay, now you can view the field capital F as being a vector space over itself always. It's a one-dimensional vector space over itself. Okay, so this is actually going to be the set of linear transformations from the vector space V, which is a vector space over the field F, to the vector space, which is the field over the field F. Okay, so let's make this more explicit then. Okay, so let's draw some pictures to try and understand this. So here, my first picture here, this will represent our vector space capital V. Okay, so what colour shall we have it in? We'll colour the vector space capital V in red here. Okay, so this is our initial vector space, which is over the field capital F, and this will have vectors in it. The elements of this vector space will be called vectors. So let's say we've got V and V bar, okay, just two arbitrary elements in that vector space. Of course, there are going to be more elements probably than just those two, but they're just two arbitrary elements that we will be using a lot in calculations and in proofs and things like that. So I've just put some arbitrary symbols in there just to have some to pick out later on. But of course, it could be much bigger than just two elements. Okay, so here's our vector space V over the field F. Now let me show you the dual space here. So I'll draw now my dual space here. So this is going to be V star, and what is going to be in here? Well, the elements in here are going to be linear maps from this vector space V onto the field F. Okay, so we might now take these linear maps phi, like so. Okay, so we'll colour in the dual space once again in turquoise here. Okay, so I'll underline it in turquoise, and here is an element of my dual space. Okay, so all the elements of my dual space then are mappings. So phi, which is an arbitrary element from my dual space here, is going to actually be a mapping from the vector space capital V into the field capital F, and this needs to be a linear map, so it needs to obey the two important criteria that linear maps must obey. Firstly, the one which relates to addition, and the second one which relates to scalar multiplication. So the first criterion is that phi of V plus V bar, okay, so when you have two elements of the vector space here, and this is why I labelled these ones up earlier, and now we're adding them together in the vector space. Now I will colour that addition in red here for addition in the vector space. Okay, we are going to see so many different additions here. We're going to have addition in the dual space, addition in the vector space, addition in the field, so it will be helpful to keep on top of it and colour the additions and indeed also multiplications in different colours to try and understand better. Okay, so phi of V plus V bar, where the addition's done in the vector space, must equal phi of V plus phi of V bar, where this addition is now done in the field. Okay, so we'll notate everything to do with the vector space V in red. Now for the field, we'll have everything, actually yellow is probably not a good colour, we'll go for vivid purple. So everything to do with the field we'll have in vivid purple. So this now is addition in the field. Okay, so we are mapping this map here, phi, will map all the elements of the vector space onto elements in the field. Okay, and one of the criteria it must obey is that for all V and V bar that you can possibly pick from your vector space, it must be the case that if you consider phi of V plus V bar, and V plus V bar will be some other vector in the vector space over here, okay, if you consider what that will be mapped onto by phi in the field, that must be the same as if you firstly map V into the field, then map V bar into the field, and then add the two of them together using the field algebraic structure. Okay, so that's just one of the criteria that this mapping phi from the vector space into the field must obey in order to be a linear map. The second criterion it must obey is that if we consider what is phi of, let's say, C times V, where C is some scalar from the field. Okay, so what you're doing here is you're multiplying the vector V by a scalar C and getting some other vector here. So in our picture here it is, and you're then mapping that onto an element in the field using this function phi here. Okay, then that must be equal to C times phi of V, and I'll try and put some colour on here as well. So here we are multiplying them together using the scalar multiplication in the vector space. So this is a vector space composition, scalar multiplication in the vector space. Here, this multiplication is in the field. Okay, that's the actual multiplication law in the field. So I'm multiplying C, the element of the field, by phi of V, which of course is another element of the field, to get a final element of the field. And I want these two different ways of doing this to give the exact same answer. And that needs to be true no matter what C you pick from the field and for all V you pick from the vector space capital V. Okay, so those are the two criteria that a mapping from the vector space capital V to the field which that vector space is over must obey in order to be a linear mapping. Okay, now if V is a mapping from the vector space V to the field which obeys these two criteria, then V is going to be an element of this set of homomorphisms from the vector space over the field F to the field F, i.e. it's going to be an element of the dual space. Okay, so you collect absolutely all mappings of this form that are in existence, and we will get a good understanding of all the mappings of this form that are in existence in this video and upcoming videos, particularly the next video where we look at the basis of a dual vector space. We'll understand we'll understand how to categorize all of the mappings of this form to a good level. Okay, so you put in absolutely all mappings of this form into a set, and that set is going to form the set that is going to be our dual vector space. Okay, so at the moment it's just a set of symbols. Yes, these symbols are representing these maps, these linear maps from the vector space V to the field capital F, but at the moment it's just a set of symbols. In order to elevate its stature up to being considered a vector space, what we need to do is define on this set of symbols addition laws and scalar multiplication laws. Okay, now we're going to make it a vector space over this same field capital F, so our scalar multiplication law is going to be scalar multiplication by elements of the field capital F. Okay, but we'll come back to scalar multiplication. The first thing I want to do is define addition. Okay, so what we're now moving to do then is firstly defining an addition and then defining a scalar multiplication law here. Okay, right, so let's start by defining addition. So I'll just put a nice title here. So we'll have addition then on our dual vector space, and I will notate addition and multiplication in the dual space by turquoise. So remember, red is for addition and scalar multiplication in the initial vector space, purple is for addition and multiplication in the field, turquoise now is going to be addition and scalar multiplication in the dual vector space. Okay, so how am I going to define addition? So let's say I have two elements of the dual vector space here, so two linear maps from the vector space to the field that it's over. So we'll have phi1 and phi2 here, which are just two maps that are in the dual space here. Okay, so how am I going to define phi1 plus phi2? And this addition here is going to be this addition in the dual space here. Okay, so how am I actually going to define this? Well, this needs to be some other element of the dual space. So whatever phi1 plus phi2 is, it's got to be some other element of this set here. Okay, so how am I going to define this? Well, the way I'm going to define it is that this mapping, phi1 plus phi2, the element in the dual space, it's going to map any vector in the initial vector space V here. So remember, all the elements in the dual space are, after all, linear maps from the initial vector space V to the field capital F. Okay, so let me define what mapping this is going to be, and then we'll make sure that that is a mapping in here. Okay, the way I'm going to define this is you just say, okay, what does V1 map this vector V onto? Now add that to what the mapping phi2 maps V onto, and of course these two things are elements of your field, so you'll have to add these two together in the field. So this is addition in the field. Okay, so if I want to know what mapping is phi1 plus phi2 in the dual vector space, I will just say, okay, it will map any vector in my original vector space V onto what phi1 would map V onto, plus in the field what phi2 would map V onto. That's a very obvious definition. Okay, but now what we need to do is check that this definition actually does work. And the first thing we need to check is that if we define phi1 plus phi2 to be this function here, we need to check that that function actually is a linear map. We need to check that this is a function from V to F that is satisfying these two criteria and therefore is in this dual space. Otherwise we've got a big problem, because it's not even going to obey the first criterion that addition must obey in a vector space, which is closure. Okay, so let's now check the axioms that addition must obey. So we'll start off with closure. Okay, so we want to make sure that the answer to this is something back within here, and that's exactly the same as checking that this function, which is a function from the vector space to the field, actually obeys these criteria and therefore is a linear map and therefore is in the dual space. Okay, right, so let's start off with criterion number 1. So in axiom number 1, we will now start by checking criterion number 1. So I'll put this as a little 1 here. So we want to check that phi1 plus phi2 of v plus v bar is equal to phi1 plus phi2 of v plus phi1 plus phi2 of v bar, and I'll just colour in the different pluses there to make this exactly obvious. So all these pluses are pluses in the dual vector space here, so I'll colour those in turquoise. Okay. This addition, where is that? Well, that's going to be addition in the actual original vector space in red here. This addition over here, where is that? Well, that will be addition in the field here. Okay, so we want to make sure that if you act this map on v plus v bar in the vector space, that it gives the map acting on v plus the map acting on v bar, where this is now done in the field, and that needs to hold true for all v and v bar. Okay, so how am I going to prove that this is true then? Well, I need to use my definition somehow. So what I'll do is apply the definition to this side here and see if I can end up with this side here. Okay, so let's work our magic on this. So phi of v1 plus phi of v2 acting on v plus v bar. Just by definition, let's apply this definition here. This will be equal to phi1 acting on v plus v bar plus, in the field, phi2 acting on v plus v bar. Okay, let's once again colour things in here. So this addition in the middle here is now addition in the field, just applying this definition here. And these additions here are still additions in the vector space. So all I've done is apply my very definition. But now what I can do is apply the fact that phi1 and phi2 are both from the original dual space here, and therefore they are linear maps. Okay, they obey this criterion. Okay, so I can split phi1 of v plus v bar into phi1 of v plus phi1 of v bar, and the same for phi2. So let's do that. Okay, so this will become phi1 of v plus phi1 of v bar plus phi2 of v plus phi2 of v bar. Now, you might say, well, shouldn't you have some brackets here? But all of these additions are in the field, and we know that addition in fields obeys associativity, so it really does not matter about where you put the brackets, so I don't need to bother putting in brackets. You can put in brackets to actually perform the computation in terms of the addition composition table. Of course, strictly speaking, you must have to do that, but it really does not matter where you put them, so I don't need to worry about brackets. Okay, right. Now, what I'd like to do then is somehow arrive at the fact that this is equal to this. So what I'm going to do is again look at my definition here. Phi of v1, phi1 plus phi2 of v is just phi1 of v plus phi2 of v. Okay, I've got those two things here, so hopefully I'll be able to bring this one and this one back together to say that's equal to that, and bring these two together to make that, just reversing the definition now. Okay, and the reason I can do this is I can apply now commutativity to this. So addition in the field will obey commutativity. Okay, so what I can do is reorder this. So this will become phi1 v1, phi1 of v, okay, plus phi2 of v, and then we'll also have plus phi1 of v bar plus phi2 of v bar. Okay, like so. And then of course what you can do is cluster this back into this. Okay, just applying the definition, and I'll just colour these plus signs in again. This is all still plus in the field, so you can collect those two things back together to make this, just applying the definition in reverse. And then you can collect these two things back together to make this, again, just applying the definition in reverse. Okay, and that's how you can take this thing and show that it's equal to this thing. So indeed, this map does obey this first criterion of a linear map. It does obey the fact that it doesn't matter whether you first add the two vectors together in the vector space or whether you first map them and then add them together in the codomain, which in this case is the field. Okay, so that's criterion number 1 checked. Now let's check criterion number 2, okay, which is all about scalar multiplication. So what we want to show then is that phi1 plus phi2 of c times v is equal to c times phi1 plus phi2 of v, like so. So let's just put some colour on here. So we'll have, this is addition obviously in our dual vector space. Okay, now this scalar multiplication here will be scalar multiplication in the original vector space, so I'll put a red mark there, whereas this multiplication here, this is an element of the field, this is an element of the field, so this now is multiplication in the field, so I'll put a purple there. Okay, so what I'd like to do then is show that these two things are equal to one another. Okay, well again this follows the exact same course as the previous one. What we're just going to do is apply the very definition of this and then apply the fact that phi1 and phi2 are linear maps themselves so that we can pull the scalar out. Okay, so let's do this a little bit quicker. So what we can now do is apply this definition here and we'll get that this is phi1 of c times v plus phi2 of c times v, adding in some colour there. This addition here will now be addition in the field. We're just applying this definition here. And of course our multiplication inside the brackets will still just be scalar multiplication in the vector space. So we'll put red there. Okay, now because phi1 and phi2 are both linear maps, because they're both elements of the dual space, we can pull out the scalar from inside the brackets to outside the brackets. So this will become c times phi1 of v plus I've missed off the c, plus c times phi2 of v, like so. Okay, where now this multiplication is multiplication in the field, because both of these are elements of the field, and indeed this addition is also addition in the field. Okay, now what I'd like to do is somehow turn this into this. How can I do that? Well, what I can firstly do is say, okay, multiplication distributes over addition in the field, so what I can do is now pull this c out, and this will become c times phi1 v plus phi2v, where this is addition in the field here, like so, and this is also multiplication in the field. So on this side we were firstly multiplying these two things by c and then adding them together. This side we're firstly adding them together and then multiplying them by c, but because distributivity holds in a field, in this case we're specifically using left distributivity, then we can factorize out the c here. Okay, now all we need to do is apply the definition in reverse again. So phi1 of v plus phi2 of v, that's the same just by definition as phi1 plus phi2 of v, and then of course this just becomes this. So we've taken this side and turned it into this side, so we have proven that indeed criterion number 2 here does apply. So addition is closed. When you define addition in this way, the answer to two of these linear maps added together is still a linear map. So what we can now conclude, what we have concluded so far, is that this is well defined. The answer is actually going to be another linear map. So phi1 plus phi2 is back within the dual space. So that's a good start, but that's only axiom number 1 that addition needs to obey. Okay, we'll have a break here, and then in the next video what we'll do is continue on with the axioms that addition must have to obey, and then of course we need to go on to scalar multiplication.